All right, so we did this in lab, but we're going to redo a little bit of what we did in lab with current and Ohm's law, and I'll show you some new stuff. So imagine a wire with a current flowing in it. Let's say that the current is going this way. So that's the direction of the positive current. The little electrons are moving in the wire, and they're actually moving this way. Okay. They move in the opposite direction of positive current flow. So they're the charge carriers, they're the little things that are free to move in the wire. And the current is defined as, this would be the average current, delta Q divided by delta T. Meaning the change in current or how much charge is passing some point in some given unit of time. The standard unit of current is an amp or an ampere. That is a coulomb per second. So an amp is a coulomb per second. If you look at a wire and you count a coulomb of charge going by in 1 second, that's an amp. All right. This is average. This doesn't have to be a constant. You can have time varying currents. Just like with velocity, we had average velocity, and then we had velocities that could change in time instantaneously. The instantaneous current, which we may come across sometime, is just dq dt. You take the limit as delta t goes to 0, and you look at the instantaneous current. Okay? So for a wire, or pretty much any material, let me give him his test. Okay. Any material that you want to talk about, the current density in the material depends on the electric field. There is an electric field associated with this charge in motion. There has to be. That's not what I want to draw. There's an electric field in this direction. I'm drawing it up here, but it's in the wire. That electric field is what's pushing the charge around. The charge is reacting to the electric field, and it's moving around the circuit. This is what a battery or power supply does. It creates an electric field in a circuit and moves the charge around. Let's say that this wire has length L. Okay. Length L. The current density, put it here, which is usually given the letter J. It is a vector. I'm not going to talk about the vector nature of J, but it is a vector, and it's equal to sigma E. And this is an area density. It's the J is the current per unit area. Okay? Sigma is called the conductivity. Sigma is the conductivity. It's the reciprocal of resistivity. In lab, we had rho, which was the resistivity. Sigma is the inverse of rho. So a large conductivity, if this is a large number, it means that the charge flows very easily in the wire. If it's a small conductivity, it means that the charge has a hard time making it through the material. Okay, it's the inverse of resistivity. In this wire, the way I've drawn it, the voltage is equal to EL. I mean, we simplified this a lot, but if you think of the potential difference along this length of wire, we know from what we did with electric fields, and the potential difference is defined as an electric field through a distance. It's just EL. I'm going to use these to make a substitution. J is equal to sigma V over L, because E is equal to V divided by L. Okay? But J is equal to I divided by the area. That's the current per unit area. We're talking about a cross section. Okay? So this is I, well, that's a big I. This is the current divided by the area is equal to sigma V over L. You can move that around and you get V is equal to, if I move this over, I get L over sigma. The reason I'm writing it as area so we don't get confused with amps times I. This has a special name. That is the resistance. That's R. Just like we had in lab, it's rho L over A. That's the resistance. Okay. R is resistance, and we can write this as V equals IR. That's where Ohm's law comes from. Ohm's law starts with this current density in a material is sigma E. And you work through that and you get to V equals IR. R has units of ohms. R is a volt per amp. It's the ratio of the voltage to the current. Has units of ohms. And the symbol is that capital omega. Okay. So I want to do a little example based on this. Oh, first, I'm going to go ahead and define electric power. Electrical power. We know that V is equal to, we know that U is equal to QV, right? That's a V. The potential energy, if you have an amount of charge and a potential difference, you pass that charge through a potential difference, that's the energy, QV. Okay? If you differentiate this du dt, that's equal to the power. That's the change in potential energy with respect to time, or rate of change. For a constant potential difference, this is equal to dq dt times V. V is a constant, let's say. Doesn't have to be, but say it is. Okay? This is, from what I wrote earlier, this is the current. And the power is equal to IV. It's just in simple DC circuits, direct current circuits where you have constant voltages and constant currents and so forth, the power is voltage times current. We can use Ohm's law to make some substitutions here. You know that V is IR, so this becomes I squared R. And I is V over R, so this is equal to V squared over R. Any one of those three is fine. You know the voltage and the resistance, use this one. If you know the current and the resistance, use that one. Okay. Sorry, can you see it? Okay. Yeah, I know when I get down here, it's hard for people in the back to see. Now I shall do a simple example. Most house wiring, stuff you would have, receptacles in your home, have pretty small wires, not very big. A receptacle would have like a 12 gauge wire coming to it. If you remember from what we did in lab with gauge, we had, if the gauge number is larger, it's a smaller wire. Like a 28 gauge wire is smaller than a 22 gauge. So normal wire that would go to a receptacle that you would plug stuff into is about 12 gauge. It can be 14, but 12 gauge pretty standard. So a 12 gauge wire has a diameter of, I got it written down here somewhere. For 12 gauge, the diameter, and that stands for diameter, 0.2053 centimeters. So what's that, about 2 millimeters? Okay. Let's say you have a length of 1 meter. And rho, let's say that it's copper. Rho of copper is about 1.7 times 10 to the negative 8 ohm meters. So what I'm going to calculate is the resistance for a 1 meter section of 12 gauge wire. R is equal to rho L over the area. So let me calculate the area. Say it's a circular wire. The area is 0.002053 meters. That's the diameter squared times pi divided by 4. And that is equal to, by my calculation, 3.310 times 10 to the negative 6 square meters. Okay, so that would be the cross-sectional area of a little 12 gauge wire. Resistance, I'm going to plug it in to rho L over A. Leave that up there. So R is equal to 1.7 times 10 to the negative 8 ohm meters, 1 meter, divided by 3.310 times 10 to the negative 6 square meters. And that is equal to what? 5.135 times 10 to the negative 3 ohms. 5 milliohms. Pretty small resistance. So let's say that I have a receptacle like that one over there, and I plug something into it. So here's some power supply. It's really AC, but okay, here's simple circuit. Here's some load, R plus minus, this is V. So it's wired with a 12 gauge wire here and a 12 gauge wire here to make the circuit, okay? Let's say that I don't know what the voltage is or that resistance, but let's say that there's 20 amps flowing in the circuit. That's not unreasonable. Most receptacles, like those duplex receptacles, are 15 amp receptacles. But you can have some that are, if you've ever seen these, which I know you have, like these little window unit air conditioners that are 120 volts, and they oftentimes will have one single receptacle. Those are 20 amp receptacles oftentimes. Just saying, let's say that I have a 20 amp current in the circuit. The power that is dissipated in the wire, for every meter of wire, there's some power loss. That's 20 amps squared times that resistance, which is 5.135 times 10 to the negative 3 ohms. And that's equal to 2.05 watts. So for every meter of wire that is connecting this circuit, if I'm using 20 amps of current, I'm losing 2 watts of power just in the wire itself. That's a loss. Now you might argue, well, it's wintertime and it's heating up the walls of my house or something. Okay, but in general, it's generally considered just a loss. It goes away as heat. In East Tennessee, they have these big power generating stations, hydroelectric, TVA, built a long, long time ago, and we get a lot of our energy from East Tennessee through TVA. And that energy is transmitted over these long, high tension power lines. There's no way to get around this loss. There's always going to be some loss. Okay, you've got high currents, you got a copper conductor, and you're losing energy just by transmitting it across the state. Not only that, you're losing voltage. You get all the way from East Tennessee to here, and that's a lot of resistance. So you have a voltage drop along the way. So these big transformer stations and other things, they do work to bump up the voltage and so forth as it's transmitted. There's all kinds of engineering problems. That's for you guys to solve to make things more efficient. Okay? Yeah. So anyway, that's the idea of power, some resistance calculations, Ohm's law. Let me ask you this. It's an interesting little observation. Let's go back to this just wire in general. Let's say that this length is equal to a meter. Let's say that this cross-sectional area, big fat wire, let's say it's about 5 square centimeters. Okay, that's like 2 by 2, a little more than 2 by 2 centimeter square. And let I, the current, equal, let's say 100 amps. So there's 100 amp current flowing in this big fat wire. The electrons are marching along here, and here comes an electron. It passes my little checkpoint here, and I put a little star on it. And I watch it go all the way down here, and I'm watching for it, and there comes my little electron. It moved a meter. Anybody have any idea about how long that takes for the electron to enter the end of the wire and move about a meter? No. I know. Anybody want to take a wild guess? Just, is it fast? Is it slow? Fast. Jenna says fast. Like, whew, moves through the wire. Well, I will tell you, it's on the order of that means on the order of somewhere around 0.5 hours. Takes about a half hour for that electron to make its way from here to here through 1 meter. So why is it that when you turn on a light switch, the lights come on immediately? They don't have to wait for the electrons to, like, you know, all the electrons are bunched up right here, turn on the switch, and then well, it doesn't work like that for one reason, huh? Somebody said something.
Is it because it has thinner wire?
Because it has what?
Thinner wire?
Thinner wire. No, it really doesn't have much to do with the gauge of the wire.
Is it the material inside the wire?
No, not really. Josh? It's the electric field. Yeah. The electric field moves really quickly. The electric field moves like a third the speed of light, depending on the material. So the electric field goes whew, and starts pushing all the electrons at once, immediately. If you've ever seen a wire burn up, I do this demo, but demos seem so difficult right now because not everybody gets to see it. I don't know. But if you've ever seen a wire burn up, it doesn't like start like a fuse and burn up, you know, or a sparkler, you light it and it kind of, no, it doesn't, it burns up all at once. That's because the electric field is pushing all the electrons at once, essentially. Okay, so you'll see the wire just poof, burn up all at once. What's happening is the electric field is making its way very quickly, and these electrons are moving, but they're having lots and lots of collisions. They're interacting with one another. They're hitting ions, they're hitting the copper atoms and so forth, and bouncing, and they bounce back and forth. But eventually they make their way. But there's lots of them. There's an Avogadro's number of them, okay? So you have plenty of electrons that are making their way through the wire. So that's the mechanism. Yeah, when you turn the switch, you're giving the electric field a path to flow, and in turn, the electrons begin to move. That's why I really don't like the water analogy. A lot of people use the water, so-called water analogy for circuits. It breaks down pretty quickly in a lot of cases because that's not what happens in fluid flow. Okay, it's something different. You have a pressure wave, a mechanical wave. Anyway. Okay. Going to introduce a new idea, something we haven't seen, related to voltage. Really is a voltage. It's kind of an old-timey, archaic term, but it's still used everywhere. It's called electromotive force. So in a real battery or a real power supply, you have, like I've been drawing since we started talking about circuits and in lab, you have this battery, okay? It has a potential to do work. It's a 12-volt battery, it's a 9-volt battery or something. But in all real batteries and power supplies, there's always some little internal resistance that is playing a role. There's always something going on internally that we can model as a small resistance where you have losses in the battery or the power supply. The electromotive force, it has units of volts. It is voltage. It's the maximum power out, it's the maximum voltage output of the battery or the power supply. When you start using it, when you start actually passing current through the circuit, this drops and the voltage that you would say measure of the output of the power supply is different than this EMF, electromotive force. Okay? Electromotive force is like the maximum output of the battery or the power supply. The little AAA batteries that you have in your calculator most of the time. You happen to know the voltage on the AAA batteries there, what their voltage is? Yeah, 1.5 volts. Their big sisters, the AA's, or the same ratio of dimensions, but a little bit bigger. Voltage on the AA batteries? Yeah, 1.5 volts. C cells, not used very much anymore. They're a little squatty, you know, kind of batteries. Anybody know the voltage on a C cell? Nobody has any experience with C cells? Used to be around a lot because we had little transistor radios and they always used C cells. 1.5 volts. D cell, those are still pretty common. D cells are the ones like in the big mag lights, flashlights, and so forth. Any idea on the voltage on those big D cells? 1.5 volts. Yeah, you see, you know how to recognize a pattern, yes. Okay, yeah, what's going on here? All these different size batteries and they're all the same voltage. Well, one thing that's going on is the D cell has more energy storage than the AAA for sure, or the C or the AA. That's part of it. But the other part of it is that the internal resistance in a D cell is going to be less than that of a AAA. This is a higher current battery. You can put more current through it, has a lower internal resistance, and you don't get as much loss with that high current. You know, little AAA batteries, they're low current. They're used in electronics, D cells. Nowadays with the LED bulbs for flashlights, they don't really require that much current, but anyway. And it's a 1.5 volt reaction, chemical reaction that is driving that battery, okay, or driving the current. Comes from a chemical reaction. So this would be the EMF of the battery. That would be its electromotive force. That is the maximum output of the battery. If you actually put the battery in a circuit and start using it, and you measure the voltage output while it's in use, it's going to be something, I guarantee it's going to be something less than 1.5 because you get a voltage drop across this little internal resistance. Okay? Let me show you an example. In your car, you have a 12 volt battery, unless you've got some, maybe you're driving a Tesla, I don't know, but let's say that it has a small internal resistance of an ohm. So that's what I'm calling little r. This would be from here to here. If I put the meter here to here, this would be the voltage output of the battery. You have to, if you didn't have a load on here, which is capital R, if you didn't have that load, then you would measure 12 volts, which if you go out and raise the hood on your car and you put a meter on it, take one of our DMMs that's in the lab, put a meter on it, you're going to measure something around 12 volts. The current is equal to E over big R plus R. We haven't talked about series circuits, but I mean look, this comes from V is equal to E minus I R. That's the idea. It's the EMF, the voltage that you get out of the battery is the EMF minus the current you're using times that little internal resistance, okay? It's a drop, it's a voltage drop. So let me give this a value. Let's say that R is equal to 20 ohms, okay? And I've already got little r is equal to 1.0 ohms. Okay. So say you're happily riding around in your car and the load that you're putting on the battery is about 20 ohms. So I can calculate the current that's equal to 12 volts divided by big R plus little r, and that's 21 ohms. Can somebody please calculate that? That's about 0.6 or so. I guess. A little less than 0.6. 12 divided by...
0.57.
Okay, 0.57. 0.57 amps. Okay, that's the current. So for 20 ohms across your 12 volt battery, which has a 1 ohm internal resistance, you get 0.57 amps. What voltage would you measure across that resistor? So V of 20 is equal to 0.57 amps. This is just Ohm's law times 20 ohms. And that is equal to 11.4 volts, I think. Not bad. Okay, you got a 12 volt battery and your actual output is about 11.4. Okay, what is that, 5% or something like that? Difference. But now, you turn on your headlights and you crank up your big bass box or whatever you call it that you have in your car. Okay. What is that thing called? Boom, 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 boom. I hear these guys riding around. Your sub, yeah, you got a huge sub in your car. So you're asking for a lot more power from the battery. Now, I haven't even talked about the alternator. We'll talk about that in a second. But you're asking for a lot. So you're loading down the battery now. So R goes from 20 ohms. Let's take it all the way down to 8 ohms. You turn on your headlights. You turn on your big base. And the load is now 8 ohms. Little r is still 1 ohm. So the current ends up being 12 volts divided by 9 ohms. What do you get for the current now? 1 point, what? 3? 4 amps? 12 divided by 9? 1.3333, okay. 1.33 amps. The voltage across the 8 ohm, okay, so all the voltage now that you're actually providing to all these things that you've got connected to your system is 8 ohms times 1.33 amps, and that is equal to 8, and the third, okay, what is that? Can somebody calculate that? I can't do it. It's 8 plus, oh, that's about 10.4.
10.64.
Oh, 10.6, okay. Yeah, you got a significant drop in output voltage. You went from 12 down to 10.6 volts. And this is what happens. This is what actually happens when you're powering things with batteries. You keep putting more load on the battery, and it's not so much how much energy the battery has, but you're loading down that battery and asking for more and more current, and you're dissipating more and more power in the battery instead of supplying it to the load, which is that external stuff that you have out there. If the alternator in your car has ever failed, okay, what does the alternator do? Yeah, it charges the battery. The alternator raises the voltage of your car up to about 13.5 volts. So it's an electromechanical device that we'll talk about in a couple of weeks that turns and creates a voltage, and it gets its energy from your if you have a gasoline car, gets its energy from your gasoline engine, and it puts an output voltage of about 13.5 volts. If you place that 13.5 volt source on your battery, it's going to force current. I'm not going to go into all the reasons, but the basic reason is you get a higher potential here than you have here, and it forces current to go through your battery in that direction. And what that's doing is it's reversing that chemical reaction that produces the 12 volts, and it's charging the battery. It's making all those little ions go back to where they came from, okay? And it charges the battery. But not only does it charge the battery, it powers all the stuff in your car. And if your alternator goes out, usually your car dies pretty quickly. But if it goes out, you're running straight battery, and you hope you can make it home. Okay? So you're asking for a lot of current, a lot of power from just the battery without the help of the alternator. Okay. That's probably all I'm going to say about that.